Now that I've covered a conceptual overview of the assumptions that linear regression makes for its hypothesis tests, and some of the diagnostic tools that people use to identify violations of those assumptions or other potential problems with linear regression models, I'm going to show you how to do some of those things in R, and I'm now working with this part of the regressiondemos.r code file. So I'm going to start by fitting one model that we're going to use for several examples. And so this is a model that has price as the response variable and two predictors, mass and battery life, two continuous numeric predictors. And I'm storing this model just with a name mod. I'm going to use it for several things. First, a normal QQ plot of the residuals. The function here is QQ norm, and the argument that it takes is any vector that you want a QQ plot for. So it doesn't have to be a vector of residuals from a regression model, but we mostly use it on vectors of residuals from regression models. And you can retrieve the residuals from an existing regression model by using the $sign operator and then the residuals object that's contained within the model object. So here is the result of the QQ norm function call. It gives us this plot. And then when we add this QQ line function call on the same vector, it draws a straight line through it. And this gives us exactly the type of QQ plots that I was showing you in the slides in the previous video. So nothing particularly concerning with this QQ plot. Our model of price based on mass and battery seems to have residuals that are close enough to normal that I'm not worried about them. We can plot the residuals against the fitted values by using a function like this. The regular plot function gives us a scatter plot as long as the arguments are numeric, or as long as we have a formula that has a numeric variable on the left and a numeric variable on the right. And so here I'm just using the $sign operator to retrieve the residuals and the fitted values from the model object that already exists. Here's the plot that we get. And this scatter plot shows nothing particularly concerning about the distribution of residuals across the fitted values. Finally, I'm going to take a look at the few highest Cook's distances from this model in this sample. And here I've just used the Cooks.distance function. And all it takes is a single linear regression model object, and it gives you a vector of the Cook's distance for every observation in the sample. And if you wanted, you could plot that vector, or you could look at the entire vector to see all the Cook's distances in your sample. But what I've done instead is sorted the vector so that it will be from lowest to highest. The highest Cook's distances are the ones we have potentially reason to be concerned about. And then I've used the tail function to just look at the end of that vector, the sorted Cook's distances. So these are the 6 highest Cook's distances resulting from this linear regression model, along with their row number in the model frame, that is the data used to fit the model. The very highest one is 0.037, which is not particularly high, so I'm not concerned about these Cook's distances either. So in this example, I used a model that fits pretty well, that doesn't violate the assumptions. I want to illustrate how these diagnostics can identify some actual problems. So for that purpose, I'm going to make some new fake variables, x and y, that have problems that we know about. So here, x has a uniform distribution from 1 to 7, nothing wrong with that. And y is the result of adding some normal noise to that x variable. So this should be a model that does not violate assumptions. Here is a plot of y against x. It looks like the points should fit a straight line pretty well. Here's a test model that is the result of calling LM on the formula y tilde x. Y is the response, x is the predictor. And here is the QQ plot. This is not a particularly concerning QQ plot. Here's the residual fitted value plot. Nothing particularly concerning here. And here is the set of the highest Cook's distances, and they don't get particularly high. Now I'm going to change the data to create some problems. The first thing that I'm going to do is create some influential points by setting the highest value of y to 0 and the lowest value to 8. So whatever the highest value of y is in the sample right now, I'm going to change it to 0. And whatever the lowest value of y is in the sample right now, I'm going to change it to 8. This has resulted in a scatter plot that looks like this. So we can see that there are two very clear bivariate outliers here. This one right here has a low x value, but a very unusually high y value. and this one has a high x value and a very unusually low y value for that x value. I'm going to fit test model again with y tilde x as the model formula, and here is what this QQ plot looks like. We can very clearly see the two multivariate outliers in the QQ plot. Here is what the plot of residuals against fitted values looks like. Again, I can see the two outliers. And here are the highest Cook's distances, and these are the values for those two highly influential points. Neither of them exceeds 0.5, which is a cutoff people sometimes use, or certainly neither of them exceeds 1, which is another cutoff people sometimes use. But clearly there's reason to be concerned about them because they're much higher than the Cook's distances of the other values in the sample. And that should lead us to investigate what's going on and notice that they have these highly unusual y values for their x values. That doesn't mean we should remove them from our sample if they're genuine responses. That does mean we should think about what they're doing and how they might be different from the other participants in the sample. Now I'm going to repeat this procedure where we know that there is a nonlinear relationship between x and y. So I'm going to keep x the same. I'm going to recompute y based on a quadratic function of x and some random noise. And here is the plot of y against x. This scatter plot, obviously, most of the time we would not want to fit a linear regression model with a straight line through this scatter plot. But if we did, we would hope that some of our typical diagnostics would catch the problem. So here is another test model that has that same model formula with the new version of y. And here's what the QQ plot looks like in this case. We can see that the observed residuals are a bit less extreme in both tails than would be expected from a truly normal distribution. But the QQ plot is not the main diagnostic tool that's going to identify this problem. The main tool is the plot of the residuals against the fitted values. And we can see very clearly this zigzag pattern, this U-shaped relationship between the residuals and the fitted values, corresponding to the U-shaped relationship between the predictor and the response variable in this case. And if we look at the Cook's distances, none of these are particularly concerning. So with this kind of nonlinear relationship, the main way that we would observe it is through this residual fitted value plot. Now I'm going to repeat with a version of y that I know has highly skewed residuals. That is, the new version of y is equal to x plus random noise that comes from an exponential distribution instead of a normal distribution. Here's a plot of y against x. You can see that the points do sort of follow a straight line, but they are much more likely to be extreme in the direction above that straight line than in the direction below. I'm going to fit the test model again. Here's the QQ plot. Very clear sign of skewness in the residuals. Here's the residual fitted values plot. This also shows the skewness in the residuals, but the QQ plot is much better at illustrating this one. And there's nothing especially concerning in the Cook's distances, although this one is a bit high, and of course if I hadn't noticed those other problems with the data, this would also lead me to investigate at least an individual data point. I'm going to repeat the procedure for a y variable that has heterogeneity of variance in its errors across the values of x. So here's a scatter plot of the new y plotted against x. We can imagine drawing a straight line through this. We can see very clearly that the residuals from that straight line will follow a funnel pattern. So if I fit the test model and look at the QQ plot, there's some indication of deviations from normality, but the easiest way to see what's going on is to look at the residual against fitted value plot, and then we can very clearly see the funnel pattern. That should be a sign that there's heteroskedasticity, and I should maybe do something about that. And again, I can look at the Cook's distances, but that's not the main tool that I'm going to use to identify this particular kind of problem, heteroskedasticity. Okay, so let's return to the robots example. And I'm going to show you a useful plotting function that can quickly give you this kind of information. So I'm going to return to this mod object that we created before. This is a model, as a reminder, that has price as the response and mass and battery as the two predictors. Here's the summary table. And if I have a model object like mod, I can just call the function plot on it. When you call the function plot and it has a single argument that's an LM object, then it automatically gives you 4 diagnostic plots in sequence. How our environment handles those diagnostic plots may vary. So if you're in RStudio, all 4 of them might get added to the sort of list of plots that you have in your plotting region. If you're in the base R GUI like I am, then it gives you a plotting window that's sort of waiting for a user response. But either way, you get one plot that is the residuals against the fitted values, along with some extra nice features drawn in, like a red line trying to trace the potential pattern, and some of the potential outliers labeled with their row numbers. This type of plot, as a reminder, is useful to look for heteroscedasticity and nonlinearity. The second plot that it gives you by default is a normal QQ plot of the residuals. This can be used to look for departures from normality, and it's like the other QQ plots that we've seen, except that it has labels on some of the more extreme values. The third plot that it gives you is that scale location plot that I mentioned in the previous video. This kind of plot can also help you identify heteroscedasticity, especially in cases where it wasn't obvious from the first plot. And the fourth plot that it gives you by default is the standardized residuals on the y-axis and leverage on the x-axis. Leverage is how far away the point is from the other points on the predictor variables. And of course, the residual is how far away that point is from the regression line. So if both of these values are high, then that's a point with high Cook's distance. And one of the more useful things about this plot is that it marks the points with the highest Cook's distance. There will be dotted gray lines showing cutoffs for Cook's distance greater than 0.5 and 1, but in this case, none of the points shown here are extreme outliers, so those dotted gray lines fall completely outside of the plotting window.